with a single pulse that travels across the seabed. Now, as it travels across the seabed, because of low aspect angle, you're going to get shadowing. So there's areas of the seabed that actually won't be insonified. And there's just a single listener. So when the returns are coming back, you have a single continuous time series that you're extracting from the seabed. Now, this graphical representation is for a single channel. Side scans, typically you get a port and starboard view. Now, the issues with standard side scan that you really have an absence of any across-track topography, so you don't really know what the shape of the seabed is. You have a single time series, so it's just a continual time series of the backscatter data, so you have to figure out how that imagery maps to the seafloor. And then the backscatter intensity and the actual bathymetry on the seabed, the correlation between those two key items is really ambiguous. Typically there's a flat bottom assumption when you're doing slant range correction, so you don't really know where the imagery fits on the seabed. And of course, the low aspect ratio inherent when you have a towed side scan causes shadowing, so there's areas of the seabed that you get no imagery from. Now here's an example of a typical side scan waterfall. So you have, time series port and starboard. This is the initiation of the pulse, travels through the water column, and then you get your first return when it hits the seabed. And this is your view. This is your view. So your entire time series, is basically from the center out to one side. So you have to determine how to map that imagery onto your underlying seabed. Now with backscatter, multibeam backscatter, you have a much higher aspect ratio. Typically the multibeams are mounted to the vessel. So your areas of when you insonify the seabed, you get a lot better coverage of the actual topology. Now, the difference is with multibeam is you have electronic focusing of beams for listening. So you have several listeners, all the way out, depending upon the width of your swath, and within each one of those beams you get what we call a snippet. So you get an individual time series per beam. So you actually have a better understanding of the correlation between the time series data and where it appears on the seabed. And of course, along with that time series is your depth solution is in that. So the great thing about multibeam backscatter is you get a time series for each beam. The bottom detection windows are overlapped, so you get good overlap of the seabed topology. And then the intensity data that you're getting back and the bathymetry correlation is unambiguous. You can determine exactly where the imagery fits on the seabed. Now here's just a quick view from GT of a backscatter waterfall. So this is made up of individual snippet time series, just not geo-corrected, but just pasted end to end. So you get full coverage. Notice as well as you get full coverage across the nadir directly below the sonar because your swath covers that area, as opposed to side scan where you have that dead space in the middle. Now geocoder, as everyone knows, or hopefully everyone knows, was a set of research code that came out of the Center for Coastal and Ocean Management at the University of New Hampshire. Was done primarily by Luciano Fonseca, and most of the industry, including IBS, adopted geocoder, and everyone had implementations of the code. Now it had a lot of great advantages. It had a powerful set of algorithms for doing the backscatter processing and some statistical analysis. It supported a wide range of sonars. The product that it produced reduced artifacts while preserving the features of the seabed, and the Mosaic provided reliable and repeatable results for the hydrographic and environmental studies. Now some of the disadvantages of the original processing were that it was very linear. It had a single file process flow, meaning you worked on one file at a time. The storage of the results of the processing resided in volatile memory. So if you had an issue, a crash, your work was gone. Processing option changes. So if you wanted to, change your output resolution of your Mosaic, you had to completely reprocess all the data. There were survey size, area resolution, and size limitations. So if you had a really large survey area, the initial implementation only allocated one big tile, so if you couldn't fit that in memory due to the resolution, you either had to change your resolution or work on a smaller area. There were issues with the user experience. Doing backscatter processing is not a simple task, and sometimes the user experience that's provided can kind of get in the way of the user getting their job done. And there was kind of a lack of robustness, so there were issues, lots of pitfalls where you can get into trouble where things would crash. Now, those disadvantages consequently carried into our own implementation of FMGeocoder. So knowing that and being aware of that, we embarked on a re-architecture of the baseline system. And in the first phase, we took the three major components, the GUI, the sonar-specific I/O, and the sonar-specific processing, and kind of tore those apart. So the first one we did is we removed the GUI and replaced it with a more enhanced workflow. Then we took the sonar-specific I/O and replaced it with our high-performance I/O library that we use with some of our other products, such as DMagic and FM Midwater. And then we took the sonar-specific processing and we divided it into generalized processing utilities and then the sonar-specific processing utilities. But the final major bit was that we then divided the entire processing of geocoder into discrete, what we call stages. Those stages being coverage, and that's when you first load a file, what the swath coverage is for a particular line, the backscatter processing, the filtering, which includes doing AVG processing and anti-aliasing of the data, ARA processing, angle range analysis, doing statistical processing, and doing mosaicing. So those were the major stages that were broken out and separated. Now the original processing pipeline for geocoder was you had a survey line, a single survey line. It came into the, basically the processing hub, and the results of that processing resided in system memory, and they only got to disk when you did an export function. So if you ever had a problem when something was happening, you basically have to start all over again. So that processing pipeline was replaced with a more generalized, what we call generalized stage processing, where you have a survey line coming in, it's accessed through high performance I/O, you have your particular processing, and then those results of a particular stage are persisted to disk. And then subsequent stages can then work off of the stage results from a previous stage. So everything cascades. And that way you're not, if there's ever an issue, you're not going to lose all of the processing that you've already done. Now for format support, the other thing we did is we kind of simplified the different pathways through geocoder. These are the primary pathways we support. .all files for time series and beam average. This is because .all files contain both backscatter and bathymetric solutions. GeoTIFFS files, because again those can contain both the bathymetric solution and the backscatter. We'll do time series and beam average for that. And then XTF for Sidescan solo. So you can either do Sidescan solo or you can do solo using it, or not solo, but use a reference bathy surface to try to aid in additional corrections. Now there's other formats that are out there that we support, but what we do is we support through those through what we call a combining stage. So for example, a lot of reson data is recorded to XTF. The backscatter will be recorded to XTF, and the bathymetry will be processed into a GSF. So what we do is we combine those two files into a new GSF file in your project that contains both the bathymetric solution as well as the time series data. The same goes for S7K files, which is the native file format for the Reson topside. So we'll pull the time series data from the S7K, combine it with the bathymetric solution in the GSF, and put a new GS inside the project. So this combining stage is done, and then you're right back where you are normally for a project, which is that you have a GSF to then process. Now here's a brief list of the current sonars we support. It's much more robust than our initial implementation. Pretty much everything that Kongsberg puts out there. There are a few left over that we're still kind of dealing with, but these can be in either the .all or some folks have them in GSF format. The Reson, the 81XX, 71XX, there's a number of ways we can get this data in. You can bring it in by pairing S7K and GSF data. You can pair XTF and GSF data, or you can pair, soon natively via S7K in our next release. Also R2 Sonic 2024, XTF GSF pair, GSF, and soon natively via the XTF format in our next release. And of course, standard Sidescan, the standard XTF Sidescan packet gets you all your other standard Sidescan sonars that record into that format, such as Klein, Edge Tech, and the GeoSwath. Okay. Now, the other big part of the re-architecture was where we did parallel stage processing. So we took our new generalized stage processing and then we parallelized that. And what that means is that, if you're running an Intel Core 2 Duo or a Quad or some of the new Nehalem 6-core chips, GT will process data in parallel to improve overall throughput. And I'll show you the results of that kind of performance. So we're doing multiple things at the same time. And that parallelization kind of went across the board to all the different stages that we're doing the processing. Now, if you remember from one of the earlier slides, these are all the basic stages that we have. The only two that actually interact with the original survey data are for coverage processing and the first pass of the backscatter processing. Everything after that uses the stage results, and those stage results are persisted in your project. And then, of course, each one of those stages was parallelized. So we're trying to maximize the throughput of GeoCoder just because of the amount of data that you're working on. Now, the results of that, this is a test data set. Some of you might be familiar with the Shallow Survey 08 data set. It was EM3002 dual head. It's about 75 lines, around 9 gigabytes of data. And these are the results from an Intel Core i7, which is the Nehalem. It's a 6-core chip, but it can run, it's hyper-threaded, so it can run 12 threads. So I built a 0.4 meter Mosaic. I did a 10 meter ARA, and this is the most computationally intensive of all the steps, is the ARA, and I built 10 meter statistics. Now, the old implementation, you'll notice, is flat, so over 2.5 hours to do that processing. And then as you add cores in GT and the new implementation, you're down under 30 minutes to crank through this data. Now that's interesting, but this gets more interesting when you're doing reprocessing. With old GeoCoder, and what I did is I left out the ARA and just said, okay, I'm going to change my Mosaic size. And in the old implementation, it's flat. You have to wait another 40 minutes to get your Mosaic out at a different resolution. With GT, as you add cores, if you're on a, and it flattens out around 4 cores here, you're down under 10 minutes to do that processing. And this is also changes to the processing parameters. So you're going through the process pipeline from the backscatter stage on. Now, if all you're doing is changing the mosaic, so you're not changing any of the processing parameters, that drops to less than a couple minutes. So an old geocoder, if all you want to do is change resolution, you're waiting 40 minutes for that data. In GT, it takes like less than 2 minutes. So the performance improvements for the parallelization are what is quite a leap forward, and kind of really are one of the core changes of the architecture for the new GT. Okay, now we'll do some demo. Any questions before I proceed, Aaron, that I should deal with?
I think most of the questions that have been coming in so far are pretty sonar specific, and Mark has been, for ones that are general, Mark is answering them and he's sending them to all. So you guys should be able to see the questions that other people are asking and the replies to that. Just for the audience, so you know, we're going to send out a poll while Mo's speaking to see what kind of acquisition software you're using for actually collecting backscatter. So if you feel like answering that, we would appreciate it. And if the answer that you want is not there, I only could give 5 choices. So you could put other, or you can ignore it. But please don't let it distract you from the important things that Mo's talking about. Go ahead.
Okay. All right, so this is GT. And what I'm going to do is I'm going to walk you through a bunch of different scenarios. I want to actually show you data being processed, so there might be some times where I have to kind of talk or tell jokes while it's processing, but I don't want to just show you movies. I want you to see the thing working, so we're going to go through some scenarios. So geocoder, GT now works with a project structure. In our 7.3 release, GT, DMagic, and FM Midwater all work off the same project structure, so they can all read and write the same project structure. So what I'm going to do is start one up, and we'll call it little 1. Now what you do after you create a project is you can add sonar data to it, or sonar files, sonar pairs. What I'm going to do for this first demo is I'm going to add some sonar files. Sorry, one of my external drives was starting up. Let's see. So you select your data. You can tell what the input coordinate system of that incoming data is. And sorry, when I kind of went by it too fast. When you create the project, GT works in projected space. So you can either let GT automatically select a UTM grid, or you can specify the projected space. The data can come in any way it wants, but the product is all in projected space. So once you load the data, the first thing GT is going to do is it's going to index all the data and extract metadata. Some of you that are familiar with our initial implementation, this was accomplished through the pre-scan pass. This is all now done automatically. If you can see it, I don't know how fast GoToMeeting's updating, but you can see the multi-core is working on the data. So this is about, this is 56 files of EM3000 data, EM3002.
Mo, somebody asked if you can make your FMGT screen just a little bit bigger, perhaps?
Sure. Yep, I'll go full screen.
Thanks.
And what it's doing now is it's actually extracting the coverage from each one of the lines. Okay, let me go full screen. All right, so here we have our coverage map. Those of you familiar with some of our other products will recognize this. It's basically the same type of view you get within DMagic. Just an overhead view of the survey area. Here we have our tree view of the input source files. Now this can be completely hierarchical, so if you want to load folders of files, you can do that. Instead of loading files, when you do the add files, you do add folders, and it can be fully recursive, and that folder structure will be maintained here. This is very similar, but now extended to what we did with the Midwater tool. You can see all the metadata related to the input files, so the type of datagrams that you have. And this is actually a good debugging tool if you're ever having an issue with a file. You can actually look to see, does it actually have seabed imagery? Does it have backscatter data? You can also get some information on the sonar type, how many heads there are, what we call the modes. These are the available modes for processing. You could, additionally you could have water column data and bathymetry, but beam time series, beam average, and then the general extents of that particular line. So this is a good, handy little tool to see what what's contained in the files that you're loading. Now, another important note about this tree view is that GT uses this view to know what it's going to work on. And what I mean by that is, if you have a line that's checked on, any type of processing that's accomplished or you request to be done will include that line. If you don't want a line to be included, you don't have to remove it. All you got to do is uncheck it, and GT won't worry about it. Now, I want to show you something really quick before we go on. I want to show you the basic project structure. So let's see. So when you create a project, you're actually creating a folder with the extension .fm proj. There's an XML file, which is your, the representation of the project. It's fully readable. You can, take a look at it to see the metadata that puts in. And then these are the key directories that all the tools work with. Ancillary data, there's an ARC folder, there's metadata, there's source data. Some of these will remain empty unless you do a step that we call encapsulation. And what encapsulation means is you can have a survey, you can be working on a survey where you have data spread all throughout your computer on different drives, and if you want to give it to someone, you can encapsulate, and what that does is it copies all the data local to your project. So all the source files will be copied into the source directory in their hierarchy. The metadata will be copied locally from the shared component, etc. Now, the key bit that's used extensively is the output directory, and for GT, the key folder is the GTB folder. So these are all files that are created that contain metadata about what GT is doing during the processing. It's not something you ever have to mess with, but if you're ever wondering, hey, what's all that data that's being put in here, that's what it's for. These are the components of the output stages that are persisted to disk after GT does its processing. Now let's see, I want to make sure I'm not missing anything. Okay, so GT kind of works in two different modes. One we call automatic processing and one we call manual processing. Manual processing is more power user, where you're going to kind of get into the nitty-gritty of the stages and potentially adjust different settings for your processing. The automatic processing is just that. You just say go and it does what it's supposed to do. There's two different ways you can do it. There's a build all button, so you just mash down on that and things start happening. Basically whatever's checked here will be created, or you can do the individual pieces. Now this view, these are all what we call products, and the difference can be seen in manual processing, and I'll get to manual processing later, is you have processing stages, so coverage extraction, backscatter adjustment, backscatter filtering, ARA inversion, and then you have product layers. So after I process the data, I want to create a Mosaic, I want to create an ARA layer or layers, I want to create a statistical layer, etc. So when you click on these buttons, GT knows what needs to be accomplished to get to the different stage. So not only are the stages broken up for the processing, but GT understands what needs to happen. So while I'm yapping, I'm just going to click all. So GT, since I requested all, Mosaic, I could have just hit the Mosaic button. GT knows that, hey, no backscatter processing has been done, So it's going to go through all of the lines and do the backscatter processing. Notice again that all of this is happening in parallel. After the backscatter extraction is done, it's going to go through the filtering stages, and then once the filtering stage is done, then it's going to do the mosaicing. So all of those are accomplished in sequence. And the knowledge of what happened, what GT processed, is persisted to disk. So GT always knows what's happening. And I'm going to show you, I'll do a little crash recovery demo a little bit later. So once we get through this, and you get some information to know what's happening, to know how long lines are taking or which line it's working on. We try to give you as much information as possible. Also, if there's any error or warning conditions, those will appear in the multi-core. Now it's doing the filtering stages, all in parallel again on all those lines. And then once that's complete, now it's going to do the mosaic. Now while it's doing the mosaic, another important thing about GT is this little panel here. This is the mosaic info panel. Now when GT loads files, it has an algorithm that attempts to automatically compute the nominal mosaic resolution, and that'll appear here. Now, if you've done the survey, you might know something about, the long track resolution. Say, 148, that's a little too small. I should bump it up, and you can change that. The statistical pixel size comes from what the mosaic size was computed as. And then these values here are very important because depending upon which version you're running, 32-bit or 64-bit, this one is kind of key. So this area, what GT needed to create the mosaic was 960 megabytes. That's not what the mosaic size will end up being because it's actually in a Fledermaus SD scalar object, but that's the memory structures that it needs to allocate when it's doing its job. So you can get a good indication of what you're going to allocate by just looking at this panel. Now if you're going to exceed memory for either for your system or for the particular build, you'll get a warning. GT will tell you, hey, I can't allocate that much. You got to change your resolution or you got to tile the data. All right, so now that the data is done processing, what I can do is I can turn off the lines. This is, if some of you are familiar with the midwater tool, this is the same histogram control that we have in the midwater tool. So I can basically do a contrast stretch. I can either click on the end and move it, or I can just left click and right click to get it where I want. And then if I zoom in, there's my mosaic. So let's see. Now another big difference with GT is you can do regional mosaics, and what I mean by that is you might load a whole set of data, and it could be a really big data set, and you may not want to process it all at once, or you may not want to generate a mosaic for everything at once. So one of the things you can do is you can do a simple area select. Let's say I just selected this area here, and let's change. Let me just show you this demonstration. Let's say 1/2 meter, and I want to generate a mosaic. Now, where our old implementation you could only have one mosaic, GT can have as many mosaic layers as you want. So I'll say no, I want to keep my other one. And what I'm doing is an inset. Now I'm kind of doing this in reverse. I'm doing an inset at a lower resolution. Really, potentially, what you want to do is if you have a really large data set, you would want to potentially do your entire data set at a lower resolution, and then areas of interest you can move in and do them at a higher resolution. Now, if I go to the Visual Objects tab, you're going to see that's where I see the visual objects that I've created. If I turn off the first mosaic, you'll see all I have is just that area that I selected. and then there they are together. Now underneath each one of these nodes you'll see the tiles. So if you have an area that's tiled, you're going to see multiple, there'll be multiple tiles of information. Let's see. Okay. All right, so that's basic, 101, easy. Let me just get right to my Mosaic without having to worry about too much stuff. And generally for all of the supported formats, if your sonar is set up correctly, there's really not a lot you have to do. GT handles most of the processing for you. So what I want to show you now is pairing. So that was loading single files. So now what I'm going to do is I'm going to load paired files, and we'll say no. And let's see, pair one. So this is where I'm going to do combining of XTF GSF or S7K GSF pairs. And I think these are my, yeah, here we go. So here's some XTF GSF pairs. So this is where the backscatter data is in the XTF file, and the bathy solution is in the GSF. The second part of the wizard is where GT is trying to match up file names. Why this tab is important is because some topsides don't necessarily use the same naming conventions. GT tries to figure out which file goes with which. In this case, they use the same naming convention, so that's great. In some cases, they don't, so what you have to do is you have to click the combo box and you have to select which goes with which. There's also an option to put a time gap. We've had data sets come through where the GSF has one timing convention and the XTF has another. So they're, might be out by a local time region of 8 hours, so you have to put in a time gap potentially. And when GT goes to combine the files, you'll get an error that says, hey, these files don't overlap in time. There's a 36,000 second time gap, which means you got to put a 10-hour time gap in here. Again, coordinate systems, and then when I click finish, what GT is doing is it's actually creating new GSF files that have both the backscatter time series data and the bathy solution, and then pulling in the coverage. Now if I go to that project, pair 1, you'll see in the output directory in the GSF file are the new GSFs. So these are the, GT leaves the original source files alone, but does create a new combined GSF that has both the bits that we need. And then the same thing here. I just say, well, that looks like a good Mosaic resolution, just smash on Mosaic. So now what I'm doing is I'm processing GSF files. So this is the GSF portion of the pipeline. Doing the filtering, doing the mosaicing, and there you have it. And these are, whoops, let me make this bigger so you folks can see, sorry about that. So these are, this is a file that has GSF data. Now, one of the other bits about generating your Mosaic is as I alluded to earlier, is you may end up in an occasion where you don't, your area is really big and you need to tile it. And I don't have a decent data set for that, but I do have a diagonal line, which is always kind of one of the keys. But I'll kind of show you two things. So I'm going to create another paired data set, but this time I'm going to pair S7K data with GSF. So this again is Reason data paired with, so the snippet data is in the S7K file, the bathy solution is in the GSF. Here's a case where the naming conventions weren't exactly right, but GT figured it out because there was a matching substring. And you get a little warning just telling you that, hey, there weren't as many bathy records as there were snippet records. This is just in case there was an issue. One important note is all of the messages that GT kicks out, if you ever want to see them, they appear here. So key message. If you get errors, the errors are going to appear in here. So they are persisted. All right, so here we have a diagonal line, the classic survey case where you've got all of this dead space. And although this line isn't that big, I'll just use it for illustration. Let's say this was much, much longer. One of the things you could do is you could go to the manual processing tab and you could select a tile size. I'll make it small because it's not a big area. Now the tiling is done, using just traditional quad tree allocation. Here's, hopefully you can see that pink outline, which is the layout of the tiles. Now you can do the tiles in either pixels, so this is image pixel size, or you can do them in meters. So if you have a giant survey area and you want 2-kilometer tiles, you can select that here. So now when I do my mosaic processing, I'm going to extract the backscatter, I'll do the filtering, and then it's going to crank through all the different tiles. So you'll have a tiled mosaic. Now, while this is processing, an interesting note is that you may have, you could have a really large data set, and we had one for testing that was, I think, about 700 lines of dual head 3002. But you can still process that data with the 32-bit version because what GT does is the data is parallelized, and when it's doing the tile processing, each tile is processed by itself. And then what happens when GT completes processing, and in the case of that data set, it was over 5 gigabytes of tiled imagery, GT will try to load as many tiles as it can if it's 32-bit and just say, hey, I couldn't load 15 of the 30 tiles, and just present to you what you have. But you can still get the data processing done. Now, of course, the way to get around that is to just use the 64-bit version. So now these are all separate tiles. If I go to the Visual Objects tab, you can see that these are all separate tiles. I can turn them on and off. So it's tiled out. So you've got a spatial allocation of the data that's a little more optimal than allocating all of that dead space. Okay. And I apologize. There's a woodpecker outside my window. Hopefully you can all hear that. I'll close my window. All right, let's see. Okay, manual, let's move now to manual processing. So let me bring up another data set. Those of you that have been in my tutorials before know the famous fish traps, which I use incessantly because it has pretty much all modalities that we deal with all our tools. Survey. So this is EAM 3002 data off the coast of New Hampshire. Get that cranking. So now what I'm going to do is show you some manual processing. I'll show you statistical generation and ARA. I'll go over some of the ARA and then some of the exporting. This data set. Aaron, any big questions while this is loading?
We've had some really good questions, but Mark has been doing a really good job of keeping up with them, and he is addressing most of them to all. Great. So you guys should all be able to see him in your questions dialogue. A big question has been when is 7.3 coming out, Mo, if you want to address that.
I'm sorry, the big question is what?
What is 7.3 so that people can get FMGT?
Soon. Hopefully. Mark would probably be able to answer that better, but we are in release candidate right now, so it's imminent.
Mark has been saying hopefully end of the week, but if not, right. Very early next week is our goal.
Yeah. Okay, let me just get this out. All right, so let's say you brought this data and you cranked out the the first mosaic. I'll show you some of the different things you can play around with. One thing I should let you know is in the preferences you have full control over how many cores you allow GT to play with. The default is automatic, so GT will use one less than the available hyperthreads, but you can override that. So that's, let me just bring that up really quick. That's here in the preferences, so you can shut it down if you want to do a whole bunch of other work. You can go to manual, or set it to 1, or you can have it use all of them. And GT will warn you if you try to use all of them. It'll say, hey, make sure you're not trying to do any other work. But in the prefs. And just to also let you know, there's a hopefully decent tutorial at the start of the manual. It kind of walks through all of the basic processing that we're doing now. So you can kind of jump into using GT fairly quickly. Okay, some of the other stuff that you can play with in GT that are similar to what you could do with the previous implementation is there's some different things you can do with changing processing parameters. You can turn off the power gain correction. You can turn off the application of a beam pattern correction. You can say, hey, I don't want to keep data for ARA. You can change your beam angle cutoffs. This is backscatter range is what geocoder and GT work in. The nominal expected range is -70 to +10. If you have a sonar that there's no defaults for and is completely uncalibrated, then you just enter those data in, those selections in here. There's settings for AVG. You can turn it off. You can change your window size. You can do trend, flat, or adaptive. Different things you can do for statistics. Different settings for the navigation coming in, which this mainly has to do with Sidescan solo and towed bodies. Things that are specific to the different formats. For example, Kongsberg, I want to use the default navigation sensor, or I want to override it. And also dual swath compensation. The current dual swath systems, there are some issues because of the secondary frequency they'll use for the other swath. You'll end up with a mosaic that just doesn't look right, that looks noisy. So what GT allows you to do is to either select the first ping of the dual swath or the second ping. And then you lose a little bit in resolution, but that resolution was mainly for bathymetry. The imagery still looks really good. And then there's all the sonar defaults. So this is all the different sonars that are supported and how they're supported and their defaults. So typically this is all handled automatically by the system. If you have something that's different and interesting, or that you want to override, you can do that. And there's an extensive section on just this part here within the manual. Also for mosaic parameters, your blending style, how the lines are blended together, the two algorithms for removing nadir. So if I said, okay, I want to try the no nadir algorithm because I know I've got reasonable coverage, and if I take a look at the the mosaic, you'll see there's a kind of a nasty nadir effect. So if I turn that or select the no nadir and just regenerate the mosaic, again without having to reprocess all the data like we had to in our previous implementation, it just takes the data that's persisted to disk and pushes it back through the mosaic pipeline. So now if I go here, actually let me just apply both the same. Nice, it's gotten rid of the majority of those nadir effects. That's over. And that's after. Another thing you can do, since this was taken, this is a midwater data set, it does pass over some suspended fish traps in the water column. And let's see if I can if I remember where it was. You know, previously, let's say you worked on a PFM to deal with the data. And that's here. Let me select the entire area and show you the cube edited. Now, most of the data has been edited out by the cube algorithm and also subsequently a little bit of manual editing. But I think right here is a good example. Yeah, here we go. So these are all beams that were rejected. So this is all the fish traps that were suspended in the water column. Now, consequently, those beams, their time series data, you know, transfers into the backscatter mosaic, and it's not necessarily something you want to have to deal with. So the way around that is to, let's go back here. I can import those edits, and I'll select that PFM. And now what's going to happen is the edits will be extracted from the PFM. Let's make sure, output GTB. And they'll appear as these EDL files. Now the key with employing PFM edits to GT is you have to make sure that your source data was in the same place. So, because GT is going to look to see how the file names match in the PFM compared to the project that you're currently running. Now, since I've added some PFM edits, I really have to go back through the processing pipeline, and this is where we get to manual processing. So I'm going to redo some of the processing before I do the mosaic. Now, to do that, you basically have to clear the state flags, and that's done through this button here, the Clear Flags button. Now, these are the major states that you can clear. You can clear the coverage, but that's fine. I don't want to deal with that. What I want to do is I want to redo the backscatter because I want it to pay attention to the PFM edits. Now, when I do that, these are all sequential stages, so GT knows that GT is going to have to redo filtering, and it's going to have to redo, you know, ARA inversion if I had previously requested that. So I'm going to say OK, and then I'm going to request another mosaic. I'm going to say no, and now notice it's going back through the backscatter processing again, so it can apply those beam edits. So what we're going to do, and it probably won't do everything, but it's going to remove a lot of these artifacts that are in the mosaic, because GT pays attention to the beam flags either within a GSF file. So if you've used other tools, shame on you to edit GSF files. It'll pay attention to those beam flag edits. If you know, you've used a PFM, or if you have a PFM that's been built from .all files, which we can't unload edit flags back to, those edit flags can be extracted directly from the PFM. All right, let me reset to the same. What I keep doing, this little trick here, is I just select one of the other mosaics and I click on the hammer icon, which applies the same histogram stretch to all. So now we have, I'll let it update. So you see some of the black, some of the artifacts have been removed. If I turn off the one we just produced, that's what it was before. So it did get rid of some of the artifacts through the beam flags. Okay. Another thing you can do, you can do a little bit of editing. Let me turn the, let's say, you have this mosaic. Actually, let me turn the other guys off so they don't show through. So, this is the mosaic I'm dealing with. And, you've got this turn, and it's really kind of ugly, and you don't like it. So what you can do is you can use the segment selection tool. And this segment selection tool is used in a lot of places, one of which is basically editing and adding. I can left mouse click to select the start and right mouse click to select the end. If I control right mouse click, it's going to snap it to the end of the line, whether I'm doing a beginning node or an ending node. So now I've selected that bit, and all I'm going to do is I'm going to come over here and I'm going to say cut segment. So what that's going to do is it's going to remove, invalidate that segment, and update the mosaic. So it was that easy. So you see that whole segment's been removed. Now, if you wanted that back, you do the same thing, just the reverse. I can add that segment back, and instead saying cut segment, say add segment, and it'll update. Now, other simple ways to update your mosaic after it's been done, you'll notice there's this real squiggly line where they kind of drove over the same part of the seabed in a real haphazard pattern. Sometime that can, have an effect on the output mosaic. But what we can do is just go to the line. Now, another quick note is whenever you're selecting lines in here, they're automatically selected in the tree view, and vice versa. So if I select a line here, I'll wait till that updates. If I select a line in the tree view, then it updates the corresponding line in the map view. If I select a line in the map view, it's going to update the corresponding line in the tree view. All right, so what I'll do is I'll just turn that line off, 1046, and let's say go back to my mosaic, right-click. Now there's a lot of power in the right-click menus. I don't have time to go over everything today. I'll show you some of the things, but there's an extensive list in the manual. And all I'm going to do is say refresh. So I'm going to tell the mosaic, hey, refresh yourself. The mosaic takes a look at what lines are included or excluded and removes those. So then the mosaic, that squiggly line is no longer part of the original mosaic. Let's see. Okay, so for other types of products, the other products that we can create are statistics and ARA. Let me just crank out a quick statistics. Statistics layers are generated directly from the process backscatter. So once my backscatter is processed, all I got to do is run the statistics and they go. This is my statistic pixel size, 5.6 meters. It's based on what the mosaic resolution was. It's a multiple of it. And then what you get in the tree view is you get all the different statistics that are created as individual layers. So as you select on them, then the subsequent one will update. Come on. And I'm waiting.
Mo, while you're waiting on
that, sure.
When you have a moment, can you talk about the creation of beam pattern files and how they're created, and also how to create a beam pattern file and apply it to line processing correction? You don't have to do it right now. I just wanted to bring it up.
Here, let's remove those. Let's put those back up again. Yeah, let me just do the ARA and then I'll go to beam pattern stuff. All right. Come on, behave. There you go. So these are all the different layers, and as I select the different statistical layers, then those layers show up. Let me do the ARA and then I'll get to the beam pattern bits. Now ARA requires what we call ARA inversion. This is where it's going to run the model to determine what the seabed type is. Now this is the most computationally intensive of any of the steps that GT does. So the parallelization of this was key to having it perform in a reasonable amount of time. So what we're going to do is we're going to extract, do the ARA processing, and different from the previous implementation of geocoder, where if you remember, the ARA was shown as a series of spheres along the track. What we actually do is we actually rasterize a surface using weighted averages based on the classification in the part of the patch. And I'll show you that. Okay. So here we have our classification. as I move over it, notice too is whenever I'm moving over the surface, you get in the status bar in the lower left, you'll get the position and then the value of whatever layer I'm going over. I mean, in this case, it's classification, so it's going to tell you, okay, this is medium sand, here's gravel, let it update. Here's medium sand, gravelly mud. And what you're actually seeing, if I click on a patch, so this is an ARA patch. There's two different ways you can actually view the response curve. This is the first. This is what we call the in-context view. So the red line is the port response curve, the green line is the starboard, and the blue line that you see is the model, so the model that's been applied. Like previous geocoder, there's a more extensive ARA dialog that you can bring up to where you can kind of play around with these values to your heart's content. If you believe it to be something else, you can do the model adjustment, and you can either apply it to that patch, or also have it just recompute the model, and that data is maintained in the ARA layer. So this is more the manual power user use of the model. Other things you can see, here's your mean outer layer, your mean var, your roughness, your impedance, etc. Basically all the layers that you want to deal with. Okay. So
Mo, I need to, can you go back to statistics a second?
Sure.
Just a question, just talk about what they mean. What are they calculated on? And they're general statistics, but what value are they used? It was used to calculate them.
They're using the backscatter value in the cell at this resolution. So all of the beams, like when we're looking at, let me turn off the ARA layer. When we're looking at the mean, this mean statistical grid, these are the mean values of the backscatter values that appear in a particular cell. So the stats are done on the process backscatter, and the process backscatter is what's used to generate the mosaic. So there's a direct, direct correlation. If I just change the transparency, you can see where the statistics overlay the underlying imagery. So they're done from the backscatter data. Is that clear enough?
I think so.
The ARA is much more complex. Okay, the ARA is much more complex. It's done through some modeling. If we want to have a little more discussion about that at the end, Mark could chime in and talk about ARA. Now, all of this data that you're creating, you can, what you might want to do is you might want to export it and get it somewhere. Now, there's a bunch of different ways to get data out. One of the ways is, you can obviously save this as a Fledermaus scene. And then if I bring up Fledermaus, you have all the layers all incorporated. So I have, I have my track lines, I can turn those off, I have my ARA layers, I have my statistic layers, and I have all of my my mosaics. So they're all embodied. So you can directly go from GT right into Fledermaus. Now, there are other types of export. Let's turn these two guys off. Let's make this a little prettier. So if I right-click on the mosaic, I could output a grayscale TIFF. I could export a surface. I could export a color TIFF, but I got to export a surface. So if you want, the Z value in an ASCII file of, say, the particular statistics, you can do that. You can export that. So, if I went to, let's go to stats. If you wanted that mean value, I want it as a surface. I want the Z value. this mean. And let's bring up. So here's my TIFF. Here's my big giant ASCII file with all the mean values. So you can extract that data. And another really important export, actually I forgot to turn it on this morning, so let me do that, is we can get this out to ARC. Let me just get ARC going.
So Mo, just with the ARC, you're calling it an export, but is it a transfer in this case, or is it different than the transfer?
No, for ARC it's a transfer. I mean, for surfaces and ASCII files, you're dealing with an export, but for ARC it's a direct transfer. So we're connecting directly to an ArcGeo database and pushing the data in. And if I bring up our catalog,
and will that require FMGIS licensing as it does in Fledermaus? Okay.
Yes. Yeah. Okay, so here's our catalog. Here's a geodatabase that I have that I previously created, but let's create a new one. Just so I have a fresh one. Traps 2. All right. So what I can do is I can take the Mosaic and I can select survey. Here's my GDB. In this case, this is a file geodatabase. Now I can either export this as a 3-band, which is an image, or I can do the single band scalar, which will just export my backscatter data and push that out. And like when you're dealing with Fledermaus, you can have a folder-based workspace, which is more along the lines of traditional shapefiles. You can have a file geodatabase, which is the one we kind of recommend. If you don't have SQL, or you can use the big SQL backend having an SDE geodatabase. So if I go to our catalog and I refresh this, there's my output data. Now the other thing you can do too is for items that, like statistics, where you have all of this, all of these different layers, I can do the whole thing at once. I can say, go to ARC, and enter a prefix name, stats. We'll select the same geodatabase, single band. We'll put a scalar out and press go. And now what this is going to do is it's going to export every layer. So I'll get my mean layer, my median layer, my min, my max, etc., as scalar objects, not color imagery objects. If you wanted to select imagery, you could select the 3-band, and that would go out as imagery.
Can you tell everyone the difference between a scalar and an image?
Sure. Scalar is ARC rasters basically are deal with what they call planes, and a single plane can be anything. It's basically a grid of values. In this case, in the case of the stats, this mean grid, this is actually a single grid of values. You export, you can export RGB, so then you actually have an image. ARC kind of doesn't care necessarily what the internal type is, because it's a grid of floats, or it's a grid of unsigned characters, or it's a grid of ints. What it does is it just tries to represent what you're looking at. But when you're dealing with 3-plane, typically you're dealing with an image. When you're dealing with one plane of data, inside Fledermaus we call that a scalar, but they are all in ARC rasters. So these are the different, rasters. And if I wanted to, if I selected 3-plane, then you'd get, the same, pretty colors that are here. It's really, how you want to use it. Let's see.
And what export options are available for the ARA? That was a question from the audience.
Oh, so the ARA, same thing. So you can do, let's do the same thing. Export to ARC. So I can do ARA here to ARC. We'll select the same traps GDB. I'll do single plane. So while this is exporting, remember that these are also individual scalar layers in a Fledermaus scene. Okay, so that's not really an export, it's kind of the native format. So all of that data is maintained, in a standard SD object. And then we have ARC. And if I go to our catalog and refresh, there's all my ARA layers, there's my depth. Here's my roughness, here's my impedance. So these are scalars that are export to ARC. You can also export them as a surface. So if I took the phi and I said export that as an ASCII surface to an XYZ, just give me the Z value, which is the the actual layer value, and I save that. Let's go back to my project. Traps 3 output, put it in here, phi. And then when I look at that, here's all my phi values in a grid. And then the last one you can do with ARA is you can export them, let's see, from a line. So I've done ARA on these lines. If I go to the source file line, I can export those as what we call the point ARA object. And this is the ARA object that we used to have with the old solution. So let me just say ARA Points. So if I load that scene back in, and then I bring in that object I just exported. Some of you might recognize, this representation. This is the older representation. So I think those are, let's see, the ARA Points, ARC, yeah, and the different types of surfaces. I think that's the key one. So ASCII, everything supported by the surface object. So as a Z value, where you get XYZ as an ArcView grid, as a series of binary heights, as a GeoTIFF if you want a floating point GeoTIFF. But these are all export as surfaces, and then ARC would be a transfer into ARC. So, all right, let me get back to one of the original questions before I proceed. Let me make sure I haven't missed anything. Export. Yeah, good. Okay, let's get back to beam pattern correction. So this is probably not a good example because this is pretty decent, but the way you do beam pattern correction in GT is first you select a segment. So let's say, and what you want to do is you want to select a segment of kind of homogeneous consistency. So this looks like it's kind of the same seabed type. So I'm going to select this segment, and then what you do is you go into the tools and you bring up the beam pattern correction dialog. Now what you're seeing is this is very similar to how we do ARA. So you have a theoretical model in the blue. You have the observed in the green, so this is the observed response, and then the correction. So you can either say, I know for a fact that that is silty sand, because you've done a grab. And since you've said that's silty sand, well, here's the model, here's the response, so that will be the correction that will be applied in the processing. Now, another thing you can do at this stage, if you haven't done any ARA, is you could say, hey, run the ARA algorithm to compute the classification. So it runs it, and the ARA says, well, that's medium sand. Now, once you apply that, this is the beam pattern correction that will be used in the processing. If I hit apply, GT says, hey, changing the beam pattern will require you to reprocess all your lines. Do you want to do that? I say yes. And then all you have to do is go to manual processing, clear flags, and reprocess. Now the other thing you can do is, if you say, hey, I wonder if I had a beam pattern correction applied, you can just go to the beam pattern viewer, and you can see it here. If you want to take it out, you just clear it, or if you have one that you've produced manually, you can load it. So that's how you get the beam pattern correction. But if you do beam pattern correction, or you load a beam pattern after you've processed, then you need to go back and you need to reprocess your lines using the clear flags. Okay. Now there's also, one of the things we tried to do with GT is we tried to create a lot of debugging tools. Now, those of you that have done any backscatter processing know that it's not always, roses and sunshine. Sometimes it's really difficult. You have a problem with your data, sometimes it's really difficult to figure out what actually is going wrong. So what we do is we provide a number of different ways you can actually analyze what you're dealing with. Most of them, if I select, say, this line, most of them are in the right-click context menu under the View submenu. So what I can do is I can say, hey, let me look at the raw backscatter. Let's say you were suspicious that the sonar was working correctly. You can interrogate the raw backscatter. So what you get is you get a waterfall window that shows you what the raw backscatter is in the file. Now, there's a matching tool to this where you don't necessarily have to have a line loaded into your project. You can actually use a tool called Examine Backscatter, and what that'll do is just let you open up some external file. So that lets you look at the raw backscatter. The other thing you can do, well, if you had beam average, you can look at the beam average. Actually, you know what? I actually have a better data set for this. I want to load because it has some issues. Hopefully I still have the project. Yeah, here it is. Kilo. All right. So this was EM-122 deep water system off the Kilmuana. Thank you, Jim Gardner. And this data, when you first process it, you might wonder, hey, should I be trying to do the beam average? Well, that line hardly has anything. If I go to this line, line 20, there's the beam average, but not necessarily that good looking because it's deep water. I can view the backscatter for that line. Backscatter looks pretty good, which is what I ended up with. If you had some other anomalies in your data that you suspected were the result of some of the navigation, you could look at, say, the sea state. What was the heave, and you get our, these are our plotting windows that are pretty much, everywhere that we do plots. So you can select on an area and zoom in, and these all work the same. So I can take a look at the heave, I can take a look at the roll and pitch to see what the vessel was doing. It's my roll and pitch plot. I can take a look at the heading, I can take a look at the power gain. There's another thing. We actually got a data set in where GT was having a hard time adjusting, doing its backscatter corrections, and the reason when we brought up the power gain plot, we saw that the power was all over the place. So somebody was sitting at the top side twiddling the knob, and there's a time dependency to how the corrections are done, and basically messing with the top side caused some anomalies in the output data, but it was easy to see. You just bring up a plot and there it is. Let's see. You can also see the result of the stages. So if you've done backscatter processing, you can view what the adjusted backscatter looks like. So this is after that first stage of processing, and then once the filter stage is done, you can have a look at the filtered backscatter. So if there's ever a potential problem, this can help you isolate where it went wrong. So if your filtering is bad, maybe you have your AVG settings incorrect. If your backscatter is bad, maybe there's something, a setting that you should change for backscatter processing. What I'm going to be doing, Aaron and I have talked about this, is there's going to be a subsequent series of troubleshooting webinars, short 5-minute little tips and tricks that we're going to post, and hopefully we're going to cover the major things that you can run into when you're processing backscatter data. And we have enough, we've encountered enough awful data that we should have plenty to be able to do some good demos for that. Let's see, I think for troubleshooting, filtered heading, pitch power, yeah, these are the main troubleshooting bits here. You can do the same plotting here, and these are for external, I think. Let me check my notes. Yeah, I think I've, oh well, actually here, let me show you one more thing. This is something that you will encounter too, and GT tries to warn you. Let me do the Kilomoana from the beginning. It's real fast, so it won't take long. Kilo 2. This is a deep water system, EM122, and one of the side effects is some of the deep water systems you have to turn off the transmit, receive, gain corrections. So what I'm going to do is I'm going to add that data back. Surveys here. Kilo. Just to show you some of the warnings that you can get within GT. So if I loaded this data, hey, my data looks like it loaded correctly, and I just said, okay, go do a Mosaic. Now what GT is going to say is, hey, you may want to turn off the do transmit power gain, and if you look at it, this is the, this is the artifact. This is the effect I get in the Mosaic, and that's because of this type of system. And this doesn't always happen with deep water systems, but occasionally it does, which is why we have the warning. And again, if that went by too fast for you, you go to the messages window, and all warnings and errors are replicated in the messages box. So I can say, hey, it's telling me I might want to turn that off. So I go to the processing parameters, I turn off our gain correction, say OK, then go to my manual processing to clear my flags, because I'm going to basically do a reprocess of the backscatter on, and then I say Mosaic, and let's keep that around just to show the differences in the output. And it's going to reprocess, and there's a much better looking Mosaic. So the difference being, let me keep a little contrast for the monitor. So the difference between this and that, and that was just a selection. Okay. Let's see. Now, Aaron, probably before I get back to more of the future stuff, are there any questions? Proceed.
Let's take a look. Mark has been catching up. He's been doing pretty good. But let's try and address a few, I guess.
Okay.
Let me see. With the beam pattern, did you actually create a beam pattern correction file that could be loaded, or did you just do a correction that was applied within the project?
No, I actually created a beam pattern correction file right here.
Okay.
Yeah, so it's if you wanted to read it, open with, where are you? Select a program. So here's the beam pattern correction file. So it's a text file. It has the beam number and the correction that's going to be applied. And then when I reprocess, actually let me bring this back up. Kilo. In your settings, if this is set beam pattern correction, applied beam pattern correction, now the default beam pattern correction is all zeros. So by default, there is a beam pattern correction applied, which is no correction. So if I create a beam pattern correction and I click apply, what apply does is it saves it to this beam pattern, this BPT file, and then clears the flags, and you basically have to reprocess. So that's where that is. And if you could also, if you remember, there was a save as, and if you wanted to save it somewhere else and load it in a future project, you could do that as well. So it does. You don't have to create it in the project. You could create one, save it somewhere globally, and then when you build a new project, you could load that beam pattern correction file in.
Okay.
Any others?
Yep. Can you clarify with the processing when you need an SD from Fledermaus and when you don't? Do you understand what I'm asking?
I think so. The only time you need an SD from Fledermaus is if you are processing Sidescan solo and you need a reference grid. So if you remember, actually let me create solo. I don't have a reference grid, but this is, let me just show you the steps you're going to go through. So let's say I loaded an XTF file that was Sidescan. And solo, I have the classic.
We're losing a little bit of your audio there, so slow down a little bit.
Oh, sorry. Okay, so I have, I've loaded an XTF Sidescan solo file, and if I created a Mosaic, this is in the solo mode, and backscatter source is solo. And sorry, I'll go full screen in a sec. Okay, so this is just Sidescan solo mode. If you wanted to correct Sidescan with a reference grid, then what you do is you select Add Reference Grid. And this is the only time that we need, well, I take that back. There are two times. One is here, Add Reference Grid. So if I actually had the bathymetry from this area, I could load it. And it needs to be an SD object, an SD sonar DTM. And then when I reprocess, what GT would do is it would pick the depths when it's doing the correction. And the other SD object type that we use, or that you can use if you have it, is a PFM. So if you want to import PFM edits. So those are the two external pieces of data that you can bring in their SD types from Fledermaus.
Okay.
Any others, Aaron?
What is the difference between characterization and classification as implemented in FMGT? That's kind of a deep question.
That is a deep question. Now, there's also another one, which is segmentation, which is image segmentation. Now, what GT tries to do in the ARA model is actually classify the substrate type. And Mark might be better to talk about this because Mark's kind of the ARA king. Mark, did you want to come on and talk about that briefly?
Sure. Just can you repeat the question? Because I was just typing there.
Sure. What is the difference?
Yeah,
we can hear you. What is the difference between characterization and classification as implemented in FMGT?
Yeah, that was the question I was just working on typing. Okay. Well, I guess I prefer the word characterization over classification because you are. I mean, what is happening is you have a model, the Jackson model of, basically the acoustic interaction between sound hitting sediments at different angles and what the backscatter intensity is, and then this model says, certain sediments have an expected waveform. Then you measure the data and you see what waveform you have, and you try and make a match of those two and say the measured waveform looks like the waveform that this set of physical parameters would generate. And to me, that's doing a characterization of that match and trying to say this is what your sediment type is. Now, the reason why I prefer that over classification is classification to me is having a jar of different materials and saying that one I can observe it and it's clearly sand, and this jar here has a bit of clay in it. So that's why I think that was a mistake early on of the terminology used to talk about ARA as classification. It's really characterization in my mind is just a better word for it. And so we're trying to sort of shift that terminology. I think that's more accurate.
So we need to change this.
Yes.
Yes. Okay.
Thanks, Mark. That was a good answer. One more question, and then we can go on to the future because we are at our scheduled end of time. How can FMGT make the real incident angle correction, and in parentheses, yes, bathymetric correction?
How can it make it?
Yes. How's it doing it?
I would probably the best place for that, Mark, correct me if I'm wrong, is to read Luciano's papers. Right, Mark?
Well, sure. I was sort of just
it's
tuned out at that first part of that question, so I didn't.
There is how it does the angle incident correction. I mean, there's a number of corrections that are done in the geocoder, the geocoder pipeline. I mean, if you want a good acoustics answer, I mean, probably the best thing to do is we'll get a reference for Luciano's paper that gives it, a good explanation. I mean, I know under the hood the implementation and what it calls, but I think probably what you want is you want a proper acoustic explanation, which will be in the paper. So why don't we get a correct reference for that, Aaron, and get that to the person asking the question. Yeah.
Okay, and let's just do one more question because it's there. Have we looked at automatic target detection?
We have not.
Are we going to?
Well, we've talked about manual target, basically, what do you call it? Like, somebody looking at the Mosaic and going, clicking on a target cursor icon and saying there's something here, and it creates a, you get a dialog where you enter the information name, and then it basically catalogs a footprint, thumbnail of what the image looks like, and sets it up that way, but nothing that's automated. Automated target detection, I mean, I've worked a little bit with that in the past. It's incredibly difficult because of the nature of the seabed. If you're over something that's mostly homogeneous, of homogeneous consistency, and there's something standing out, that's a little easier to do it through standard image processing techniques. But automated target detection is complex. Now, with that said, that's a good segue into the future of where GT is going. Is GT is a platform by which, if you have such an algorithm, what you'll be able to do is you'll be able to create that as a plugin that can be used. You can sell it or widely distribute it, and then GT can just use that natively as a plugin tool for processing. But currently there's nothing for targeting in an automated fashion. The only thing we've thought of is just adding the addition of a cursor. It's basically an operator going through and saying, something of interest, something of interest, something of interest, where it just creates a contact list, basically. So with that good segue, let me bring this guy back up. So where we're going on future enhancements, and of course, future enhancements always include, hey, there's a new sonar, bug fixes, extra features people want. But a lot of the keys to the future are going to be accomplished by what we call our new plugin architecture. And what the plugin architecture does is it gives a third-party developer, these folks can be at universities, it can just be a single person that wants to write some code. It gives them direct access to major components of the GT pipeline. This is the GT data structures, the high performance I/O, so they don't have to write their own I/O package. They can use GTs. They get access to the generalized processing routines, and then they can basically replace pipeline.
Mo, you're going a little.
Sections, what we call
Mo, can you hear me? Your audio is breaking up a little bit, so just take it nice and slow so we get most of the words. Thanks.
Okay, sorry. Okay, let's go here. So there are two what we call tiers, Tier 1 and Tier 2 plugins. Tier 1 plugins will appear in the GUI menus. So for example, you could have import-export plugins, so they appear in the context menus of GT's tree views. Same with the export, and also you could have whole new tools that appear. You could create a standalone tool such as an automated target tracking utility that runs with its own full GUI if required. The Tier 2 plugins are plugins that can replace specific components of the processing pipeline. For example, if a new sonar comes online and it requires a different set of backscatter corrections, we don't have to release a whole new version of GT. All we do is build a new plugin for the corrections for that particular sonar. Now the way these work is the import plugin, you can use GT's I/O, and then you can import to what we call an FMGT file, which is GT's native backscatter processed format, or you can create an internal GSF, and then GT does what it normally does. It just processes that data like it would in any other project. The other thing you can do is you can build export plugins, and where they appear is they appear in the context menus of the different types of components. So this is here's an export angular response plugin that was added from the right-click menu. And what happens is when GT starts, and I'll show you this, when it runs, it looks in its plugin folders, it loads all the plugins and connects them to the parts of the GUI based on their particular plugin type. This is one for Mosaics, just an export demo. If you want to export to some other format or your own custom format, then you could just write an export plugin. Same for statistics, and the same for ARA. These are all different plugin types that you can use. The other thing you can do is you can create a tool, a custom tool. So those appear. We've already started just to play around with some. Those can appear in the tools menu when they get hooked up, and then there's also a manufacturer name. So if if it's done by a particular manufacturer, then there's a submenu based on the manufacturer. So if we had a bunch of CCOM plugins, then there'd be a CCOM submenu with all the plugins that they've created. Here's just an example of just an acoustic workbench we're playing around with, but it's this is a separate entity that runs by itself, but that talks directly to the application. And this is just another simple example of a sound velocity profile viewer. Now the Tier 2 get a little more interesting, can actually be put into the multi-core pipeline. So as I said, if there's a new sonar that comes online and it needs a specific set of correction algorithms, or CCOM says, hey, we are changing the geocoder base corrections for Kongsberg sonars, then all we do is swap that out with a corrections plugin, and then that plugin is called directly by the multi-core pipeline. So there's no loss in performance, and adding a new feature is basically putting a plugin in a folder and restarting the application. And then here's the example of the process configuration. So if you want to select a plugin that's going to be used for a particular part of the stage processing that's not the default, say the sample R2 Sonics 2024, you just select that, and now that's part of your configuration. It's saved and persisted into your project, and now whenever you work on that project, you're going to be using that custom plugin. And yeah, let me show you that really quick. Have that go away. Okay, so here is the plugins folder. Here's a bunch of DLLs. So when I run the plugins version of GT, let's bring the straps up. You'll notice there's some plugins here. If I go to the right-click menu, there's some plugins here. I can export. This is actually what's fun is it makes creating debug tools for your data really easy. We had some data where there was some weird things happening with the GSF beam flags, so we just wrote a plugin to export those flags. Import plugins. Here's a bunch of import plugins. So direct R2Sonics XTF to GSF, S7K direct, Reson XTF direct, and Fishback. And those are all, these are all the plugins here. So now notice, what I want you to notice is notice the tools menu, right? There's two tools, batch indexer and the SPP viewer. So what I'm going to do is I'm going to turn off the application and, whoops, let's go back to my folder. And I have a new plugin, this Acoustic Workbench DLL, and I'm going to copy that into the plugins folder. And then I'm going to restart the application. And go to my tools menu. And now I have the Acoustic Workbench folder. So it's that simple. When the plugin is created, you put it in the plugins directory, you restart the application, it hooks up. It didn't require us to create a whole new binary of the GT build for you to download. You just drop it and it works. And this was that simple. Just like a mock-up of a tool that has a complex UI. Basically lets you select plot, beam backscatter versus power. You can take a look at, what the bathymetry is versus what the backscatter is. So just a simple demonstration that this is a complex, this is a complex plugin that has a custom user interface that's talking directly to GT. So this is what's coming. This plugin interface will be public for download. There's already guys at CCOM working on plugins for GT, and it's the primary reason why I call GT a platform as opposed to an application. It's not a fixed application that does a specific job. It's a platform that has a job whose intent is to be expanded to have more capabilities over time through the plugin interface. So that is that, I think, Aaron. Are there any further questions? I think I've covered all my things I wanted to cover.
I think so. Mark is addressing most of them, but just generally, just to clarify, the plugins come post 7.3, so you can't.
Correct. They are 7.3.1.
7.3.1.
Right here.
So
yep.
Even 7.3 is not out yet, so 7.3.1 is further along.
Yep.
We had a question about metadata generation with plugin usage, and I think that could be a good general question. Are we maintaining any metadata when you change processing parameters or anything like that with GT?
Yeah, it's all maintained. Well, all of the processing parameters are maintained in the project. When the files are loaded, there's metadata that we extract during the indexing process, and that's saved in a shared location on your system, or it can be saved within your project if you don't want it to be shared. You can save it within your project, but let's bring this back up. All of the processing selections, all of these selections in this dialog, in the processing dialog, in the Mosaic dialog, projections, all of that stuff. Actually, probably the best way to show you is to show you what the XML file looks like, and it'll be a little clearer. Let me bring one up really quick, and then you can see how it's laid out in the metadata. Traps 3. So this is a view of the project file. So there's a specific project configuration, and this is related to GT. There'll be a line for DMagic, there'll be a line for FM Midwater, but everything is maintained in here. So is there dual swath compensation, what the AVG window size is? This is all XML and it's all readable. So if you had to mess with it, you could change it in a text editor. And when you reload the system, it would say, hey, my statistic pixel size is now 7, not 10. whatever you want to change it to. So, including the georeferencing, this is all maintained in here. So that's the project file is the key, the key to the processing metadata. The persisted state, the stage results occur, those are all in here and are not readable by the user. These are binary files that are used specifically by GT. Now, with that said, if there was something specific you wanted to get at, like I showed you, like the beam flags, or you wanted to extract the sector frequencies, you could use a plugin to extract and dump to an ASCII file the number of sectors per ping and the sector frequencies per ping, because you could use the high-speed I/O interface through the plugin interface to get you all that data. So there's a lot of stuff that you'll be able to do in 7.3.1 when the plugin interface hits. That's pretty extensive.
Okay. I think the main suggestion we're getting then for that is to make sure that if a plugin is used, that it is documented somewhere in metadata that people can see that plugin A, B, or C was used to process, this data. So.
Oh, that is here.
It is.
See. So it's being specific. Yeah, well, it's not in the 7.3, but when you do, let's go back to this. When you do this part, configuration, so if I select, the R2 Sonics corrections plugin, let me make sure, I have two versions of this running, which is always bad. Settings, config. Or I'll say it's, let's leave it at that. Then that plugin that was used, let me see if I can actually find it. There it is here. So plugin adjust sonar corrections is the GT corrections R2 Sonic. Oops, sorry. Does that answer the question a little better?
Yes, as far as I'm concerned. That answered the question.
Yeah. So it's specifically in the project file. So when you restart your project, that configuration is maintained for sure. Okay.
I think that's all the questions. Did you have anything else you wanted to talk about?
No, thanks for sitting through, close to 2 hours of me yammering on.
We did get our poll results. I'm sorry that the poll blocked everybody's screen. We never ran one of those before, so we'll be more careful next time. But it was only up for a few seconds, but 51% of people voted, and 31% of people are using HiPAC, 23% are using Quincy, 5% are using PDS 2000, 31% are using SIS, and 41% are other or didn't know the answer. So thank you for those people who got to answer that question very quickly. The questions that needed more answers, if Mark just told you he would get back to you, I will make sure that Mark sends you a really good response to your more complicated questions. So we will get back to anybody who wasn't fully addressed via email afterwards. Thank you all again for attending, and hopefully we'll see you on our next webinar, which there should be one in July. I'm not 100% sure because there's a lot going on in July, but it will be up on our events page and you'll receive emails. All right. Thanks, Mo.
Thanks.
Thank you, everybody. Bye-bye.